Okay guys, in this video lesson we're going to take a look at impulse and what it means to apply an impulse onto an object, okay? So first thing we want to look at is this term impulse and make sure we have it down exactly what that means to us, all right? So in the world of physics, which is a little bit different than our everyday speech, if we have an impulse, that's a change in momentum, all right? It's that simple. It's anytime we change momentum, we have an impulse. You could take the word impulse and the phrase change in momentum and completely interchange them. So what that means is anytime we're changing a velocity because we're changing momentum, we have some sort of impulse that is acting on our object, okay? Mathematically speaking also, we'll get to the formula here in a second, but we can solve for the impulse of something, or I could ask you, solve for the change in momentum. They mean the exact same thing, okay? So as we move forward here, anytime you see the word impulse, think of that means change in momentum. It's not that different really than how we said a change in velocity meant acceleration. Same idea, okay? Now, moving forward that, we need to use the impulse momentum theorem, which basically says that if you're going to change the momentum or if you're going to apply an impulse onto something, you need to apply a force, and that force must act upon the object for a finite amount of time. Okay? What that means to us is if I want to change the velocity of something, which will in turn change my momentum, I need to apply a force. This really is nothing new to what we've been talking about before, because we already know that if we apply a net force on something, that means we're going to have an acceleration. Well, an acceleration is a change in velocity. Well, a change in velocity, if we apply mass to that, also then gives us a change in momentum, okay? Now, mathematically, we can derive all this information out. So let's take a look at it. So our force we know is m times a, but a is our change in velocity over change in time. So we can insert delta v over delta t for a, and we can say that the force you apply to a mass will equal a mass times a change in velocity over a change in time. Well, just rearranging that, we can say a force applied over a certain amount of time equals a mass times a change in velocity. Okay? Or broken out, we see velocity final minus velocity initial. Well, if we come back here, mass times change in velocity is really not that different than momentum times mass times velocity. So since our momentum equals mass times velocity, and our change in momentum then could be attributed to being a change in velocity. So one step from here, we can say anytime I change momentum, impulse, I had to take my mass times my change in velocity. Well, that's really no different than what's up here. So now we get to the last piece of this kind of theorem, or this idea, is that if you apply a force through a certain amount of time, you're going to change the momentum. Okay, either version of this equation will be used in our math. All right, so let's take a look at some concept checks here. We're gonna watch a little video, and in the video, this young fine man here is going to be throwing an egg into this sheet. Here we go.
Anytime.
All right, so what we see here in that very last throw, okay, the egg broke, okay? So why did the egg break on the last throw? Okay, and then what changed about this? So take a minute and think about it. Pause the video maybe, and we'll come back and talk about it. All right, so if we think about this, the only difference in all the other throw is it hit the wall. Now the wall doesn't move as much, and as a result, the time it takes for that collision to occur was much shorter in that last throw. So as the time went down, okay, so time went down, the mass of the egg stayed the same. It went from, he threw it just as hard, so the velocity change stayed the same. So time went down, so force had to go up. Force went up enough to a point where he is going to break the egg, okay? So time is our big change difference here as we take a look at this, all right? Now, what about applying brakes to a car? If you apply the brakes to a car with double the force over the same amount of time, what happens to the impulse of the car? Okay, double the force, same amount of time, we should double the impulse or double that change in momentum. All right, there is a lot of engineering gone into sports equipment and other type of things trying to use this concept in terms of making their products better. So the longer you can put, for example, the egg example, the longer you can keep contact between, let's say, a golf club head and a golf ball, or longer you're in contact with your hand to a volleyball, those times increase. Your body can only generate a certain amount of force. So as a result, you actually can hit something farther, hit something harder, hit something faster. Okay? It's about keeping your contact longer if you want things to move away faster. Okay? It's also one of the reasons why coaches say follow through. Because if you follow through with a swing or you follow through with a strike, that kind of stuff, the result is you have these minor amounts of extra time touching the ball, touching the object, and that can create more momentum change or create more impulse. Okay? Crumple zones on cars are the exact opposite of this. Where in a crumple zone, we want the car to crumple up into this tiny little ball of twisted metal because we want the collision to last as long as physically possible when we hit something. Now, the cab of the car, that stays rigid to protect you, but the rest of the car gets destroyed. And that's by design because it really wants your time to go up so the force that we feel is much less on this. All right, so let's do a little math check now. We have a 2 kilogram kickball rolled at 5.44 meters per second. After being kicked, it now moves at 7.88 meters per second. Now notice, it was rolled to the east, and then afterward it was moving to the west. So it was the opposite direction. So make sure you get your signs right. What's the impulse on the ball? And if the contact with the ball is 0.15 seconds, how much force was put on the ball? Okay? Pause the video, work it out, unpause it, we'll see how we do. Okay, so here's our first one. The impulse is the same thing as change in momentum. Okay, so we're not really worried about force right now or time. Okay, so we know the mass of the ball, we know the final velocity, we know the initial velocity, so we plug them in. Notice how I made west positive 7.44. I made east negative, so we're subtracting a negative 5.44. So my change in momentum, because I made west positive, is 21.2 kilogram meters per second. Now, if you flip that, if you made east positive and west negative, you would have gotten a negative value here. Okay? One way to combat worrying about positive or negatives is answer this, which I didn't do, but you could have wrote 21.2 kilogram meters per second west, because this is the direction that is our positive direction. Okay, that's actually probably better if I would have done that, to be honest. Now, contact with the ball was 0.15 seconds. So if we now take this idea, we know our change of momentum, and we know it's force times change in time. So the force we get is going to be our change in momentum, which we already solved for, divided by our time. So we're going to get a force of 141 newtons, okay? And it should have the same sign because if you're going to put that much force on the ball, it should have it move off in the same direction. So we have 141 newtons to the west, or a positive 141 newtons of force applied to this, okay? Now, that's just a couple examples of how we can use impulse. In class, we'll have more for you. Thank you.